Okay, so welcome to this next video, which is on logic, sort of our introduction to logic and circuits. So there may or may not be a second a second video for this. So I've called it part one, but it might be part one of one. But we'll see. So right, so where are we in our story? Um, So we've certainly binary by now we know is the king, and we've spent obviously quite a bit of time on how to store things in binary, and then the most recent um, video we talked a little bit about more about the sort of infrastructure of how the computer is kind of wired and the physical uh, principles and physical mediums for memory. So the last piece, though, that we really needed to talk about is to talk a little bit about the sort of physical way that a computer actually does things. So, and by that I mean physically does things. At this point, we've really just been talking more about um, mostly about memory, which is certainly important, and there's certainly a lot. Obviously, there was a lot to say about it, but memory as an object or as an item is sort of a static item. It's okay, fine, zeros and ones, and they're stored, and okay, that's great. But a computer is more than just a repository of data or of bits and of memory. It's actually an object that does things, that performs tasks, right? Um, so programs, right, which we know is just a series of instructions, that's fine. Um, and each program is just a series of bits, or a sequence of bits. Each instruction is also going to be in binary. But really, the question is, okay, fine, fine, fine. So it knows how to run. Right now, I'm running PowerPoint, right? Microsoft PowerPoint. That's a program. So sure, did the writer of PowerPoint, um, Bill Gates or whoever wrote the program for PowerPoint? Sure, all those commands that they wrote in order to say do whatever PowerPoint's supposed to do. Sure, that's all binary also. But how does it actually know to do stuff, right? And when does it know? And what is the sort of mechanism to say, all right, I got to introduce sort of the timing element and the actual action of all the things that a computer does. So that's really what this unit is all about: is how do things actually physically happen? And of course, maybe not surprisingly, the answer is it's also a binary system, but it's not binary in the sense that it's not just zeros and ones like we've been thinking about them in terms of data. It's an actual sort of circuitry, which also is going to turn out to be binary, that makes things actually happen. So this is sort of the more physical and almost the more physics kind of perspective um, on computers and how computers work. So, and this is not going to be high level whatsoever. I know you all probably took a physics class of some sort in high school, which probably had you doing a variety of things. I think back in the day, probably, maybe 20 or 30 years ago, especially, physics classes involved a lot more in the way of sort of electricity and how does electricity work and things like that, which probably now I don't remember doing any of that in high school physics, mostly probably because it was a, a legal liability that you don't really want people playing around with electricity. But anyway, just some basics of how electricity and circuitry works. um, I think maybe we all know this, that an electrical circuit works, which a circuit's just a term for a linked um, circle, I guess, of electricity, of wires and electricity. So, how does electricity work? Is that you have a path of wires or whatever, and if you pass electrical current of any sort, from a battery or from an outlet, um, the completion of a circuit is what makes electricity pass through it. So how do we not just sort of have electricity all the time? Let's think about a light switch is sort of the best example of an easy electrical circuit. So in whatever room you're sitting in right now, there's probably a light switch on a wall or on a light fixture. And so what's happening right now? Well, probably the light is on unless you're watching this video in the dark, in which case you're kind of strange. Um, right, so why is your light on right now versus off? Well, there's wiring, of course, so you probably know that in an in a light switch, there's wires, of course, that flow in and out of the light switch. And they are ultimately, of course, connected to the light bulb or light fixture that's in your room. And when the light is turned on, what makes it on is that when you flip the switch, you complete a circuit. In other words, you make a complete circle of electricity. So there's wires that are in the switch. When you turn the switch on, the wires that are in the switch connect to each other. And that makes a complete cycle of wiring that goes to the light bulb, ultimately, in the fixture. And since it's all connected, the electrical current passes all the way through it, and that's what makes the light turn on. So what makes the light turn off? Well, when you flip the switch off, it quite simply takes the two ends of the wires that are in the light switch and it breaks them, or makes them not meet, which breaks the circuit, and that causes electricity to not make a complete cycle. And this is why your light turns off when you flip the switch. Okay, that's the basic um, principle of electricity, right? So this is the idea that if you didn't, if you got struck by lightning in midair, you'd actually be fine because there'd be obviously a lot of electricity flowing through you. But since you're not connected to anything, if you're in midair, there is no actual sort of charge, so you'd be fine. Now, of course, if you're standing on the ground and electricity strikes you, that can then, of course, complete the circuit between you and the ground, and it shoots back up into the sky, and that's why, of course, you're in trouble then. Okay, right, so that's the general idea of an electrical current. So what's in an actual sort of circuit, and by circuit maybe now I mean more so in your computer and in electrical or sort of computer devices. Well, we have the same ideas that obviously you have an appreciation for the fact that your phone or your laptop has electricity flowing through it, right, through the battery or through that it's plugged in, right? So how does it know, so okay, fine. So that's true. Well, in the logic in the CPU portion and elsewhere in your computer, you also have what are called transistors. And transistors are light switches, basically. Okay, so it's a transistor, which I have a picture of it on the next slide, is just a fancy word for a spot where you can either break or connect electricity. So it's basically a light switch. Now, I don't mean a light switch in the sense that your screen you're looking at right now is lit. I mean more a light switch in the sense of that there are wires all over your laptop that are circuits that can either be connected or disconnected at these so-called transistors in order to make things happen. Right? So action, so to speak, when you say your computer does something, meaning, things are in motion, right? Or whatever actions are happening. These are attained, or these things are produced simply by the correct switching of transistors from on to off or off to on. Obviously, these things happen very quickly and we don't really notice them. But, I'm moving the mouse right now, right? That's an action, obviously. I know we sort of say, oh, that's my finger that's touching the trackpad and moving the mouse. Okay, that's true. But of course, physical motion, right, has to be generated somehow. So how does it know? How does your computer know to make the mouse, move around in a circle like this? Well, obviously there's on the trackpad that I'm moving with my finger right now. There's an electrical current, and depending on where my finger touches, it's completing or disconnecting certain transistors that are corresponding in the computer to say, oh, he moved his finger to the left, so you need to move the mouse to the left. And those circuits are getting connected and saying, oh, okay, move it, move it, move it, move it. And then when I stop moving my finger, those circuits turn off and say, okay, don't move the mouse anymore. That's the basic idea of how any sort of action is happening. Okay, so these are called, right, so that's the idea of just a general idea of an electrical circuit. When we're trying to say, what do these circuits do to kind of regulate the computer and regulate the actions of the computer, we might call them logical circuits. Okay, so as I said a second ago, right, this isn't all that important, but a transistor, which there are, I don't know, millions or probably billions of transistors in your computer and in your phone and everywhere else, is just a fancy word for, again, the idea of a light switch, that you have electricity that's flowing in this wire, and it goes into the switch, into the transistor. And if it's connected, if it's closed, electricity will flow through this gate and out the sort of output, or the fancy word is source and sink. So if you have your transistor turned on, the electricity that comes into it connects and is allowed to flow out of it, which would sort of complete a circuit. On the other hand, if you flip the switch, if you flip the transistor, which visually would sort of look like this black would sort of be up, right, and disconnect these two blue wires, then electricity which is flowing in will not be allowed to flow out. And in that sense, this circuit is sort of turned off right now. Okay? So it's just a basic idea of a light switch. So the circuitry in the computer is just made up of a whole bunch of these transistors that are turning on and turning off and turning on and turning off, all the time. Anytime your computer is actually doing anything, which is all the time, but even, especially when you're interacting with it and you're doing stuff and you're typing or you're, doing internet things or whatever, even just moving the mouse, lots of circuits are firing on and firing off. So what's this idea? So remember, of course, a computer is, if you really want to try to say what is the purpose of a computer, or what's the idea, the general design principle of a computer, is that it's supposed to be as much as possible like a person, like a human being, right? So we've talked about the CPU of the computer, that's like our brain, where in terms of processing things. Computers also have memory, which is also sort of our brain. There's input devices, like a mouse or a trackpad and a keyboard. Well, we have input devices too. We have eyes and we have ears and things like that. Okay, output, okay, et cetera, right? So, of course, a computer in general is trying to be a human as much as possible. So what's all of this stuff with circuits and logic and whatnot? This is the portion of the computer that's trying to mimic our physical action as a person. So how do we do these things? Well, as a human, right? How do I make something happen? Well, the same idea is going to be true in a computer. How do I make things in a computer happen? For example, I push keys on the keyboard. That would sort of make things happen. Or I move the mouse, or I put a disk in, or whatever, right? These are all ways in which I click on things, right? That makes things happen. And that's my way of sort of sending a stimulus, a stimulation to certain parts of the computer that are going to say, oh, okay, he clicked on that link. I should launch a browser and go to that website, right? So that's the idea, right? I communicate, I stimulate things to happen through mouse, through keyboard, etc. And in our bodies, how do we do this? Well, we say, I mean, I know we don't think about this a whole lot, but how do we make action happen in our own bodies is actually the same principle, right? We get an idea in our brain, we send a message through our nervous system to our muscles, and that causes our hand to move up. So if I try to think about it, I know it just comes as second nature to us, but if I'm trying to say move my right hand from, down to up, I send signals. I send sort of electrical, to a degree, signals from my brain to my right hand that says, okay, move up now, right? How many of you just moved your right hand up? Probably a lot of you. I just did it 3 or 4 times, right? It's the same idea, right? I need to sort of say, all right, action is stimulated by some input, and then I want to connect all the sort of parts in order to produce the desired output. Same idea in a computer. Okay, so in order for us to kind of understand a little bit about this, obviously this is probably something you can appreciate is very complicated, right? In order to have, even just in your small phone, right, which is a few inches by a few inches, there's all kinds of circuitry in there. And of course, it's amazing, right, that we've come this far. And computers from 50 years ago, which had circuits, of course, in them just like we do now, they were enormous. And they also didn't do a whole heck of a lot. So we've gotten extremely good at making very, very complicated circuits in small physical spaces and being able to put all of that amazing nanotechnology in a phone. So, okay, but we can appreciate that that's probably very complicated. So what we want to do here in this unit is try to at least get a little sense of, for obviously for basic things, or what's the general idea of the logic and the circuitry. And so for that, we introduce a little bit of terminology here. That in logic, in general, how does one try to sort of say, okay, well, what does this circuit mean? Or what is, how do I sort of tell this to do what I want it to do when I want it to do it, but not when I don't want to do it? So, in order to try to sort of study the general idea of logic, um, here's some easy or some basic terms we might use. So, we're going to have things called propositions. And usually in math or in computer science, you just use maybe capital letters to represent these things. And what are these? These are just statements that are either true or false at any given time. All right, and we'll do lots of examples of these, but and then we'll use this usual binary notion that a 0 corresponds to false and a 1 corresponds to true. Okay, so proposition might be something like, is the spacebar pressed? Is the monitor on? Am I connected to a printer? These are all things that are good examples of propositions because they're either yes or no, or true or false at any given time. Okay, so those are sort of the physical components, I suppose, of logic. They're either true or false, and I want to sort of put them together in a way in order to cause, more complex actions to happen when they're supposed to happen and not happen when they're not supposed to happen. So I'll connect propositions with things that are called logical operators. So these are used to connect two or more propositions with these logical connectors or operators, as they're called. We're going to highlight 4 examples of logical connectors or logical operators: not, or, and XOR, as that would be pronounced. So I'm going to tell you more about what each of these is on the next slide. So, okay, I'm going to connect some of these. They're English words, obviously, except for maybe XOR, but these guys are English words, so you can probably sort of guess a little bit about what they might be trying to convey. All right, so I'm going to take propositions, I'm going to link them together with operators, and I'm going to form sentences. So what is a sentence? Are some propositions that are connected or linked by logic operators to form a sentence or a statement that's hopefully going to describe some sort of task. So in this example, I say X equals A and B or C. Okay, so maybe we don't know exactly what these things mean yet, but this is an example of a sentence, this is the main object, or these are the main types of objects I'm going to try to study then and say, okay, this is a sentence that describes, for example, something like, when do I produce a capital W? Or maybe this describes, when should I turn the computer off? Well, if this sentence is true, then yes, you should turn the computer off. If it's false, then no, I shouldn't turn the computer off. Stuff like that. Okay. So, I'll show you a couple ways that we're going to try to sort of examine or develop these sentences. But the most basic idea to try to sort of understand what one of these sentences relates to, I guess, is to analyze it through what's called making a truth table. So a truth table, this is sometimes more awkward to describe in words, so we'll see this in action. But what is a truth table? So a truth table is going to be a table that's going to hopefully tell us when a sentence, a logical sentence, is true and false. In other words, when will this be on and when will this be off? Or when will this happen and when will this not happen? So in order to make one, we're going to literally just make a table. And what is it going to consist of? So first, it's going to consist of all the propositions in our logical sentence. So A, B, C, whatever we have. And as well as any combination of them should be columns in our chart. So we'll do examples of this if this isn't clear. So then what are we going to do? So then we're going to say, all right, I'm going to make a bunch of rows in my chart, And what is the first thing I want to do is I just want to run through all the different combinations of true false for all the propositions in our sentence. So we're not going to usually do more than three, maybe occasionally four, but two, three, or four is probably plenty for us. So we're going to make a list or make rows for all the different true false. In other words, I might say, okay, what if A is true and B is false and C is true or something like that. Okay, so I'm going to fill those in first. Okay, then what's the actual thing we need to compute or consider? We want to consider and fill in all the true false values then for all the logical expressions and the whole sentence. In fact, in every row of my chart, since this will correspond to, well, is my whole sentence true or false, on or off, in all the different true false possible scenarios. Okay? And if possible, probably maybe at the end we can try to sort of summarize and say, okay, I've analyzed this, and here's my summary sort of when is this sentence or when is this logical circuit true or false? What action or meaning does it represent? Okay, this is awkward to describe in words, so let's move as quickly as possible to some examples, which will make sense. This isn't that hard. It probably sounds crazier than it is. All right, so before we make our tables, let me tell you just a little bit about our four logical operators, or our logical connectors. So these are the four. So not is, this just represents the sort of reverse or the opposite operator that is going to take anything that's true and make it false, and anything that's false, it's going to make it true. So again, think about this as sort of being in the sequence of a circuit. If you throw a not into a circuit, it's going to just switch it to the opposite of whatever it was. So if it was on, it's now off. If it was off, it's now on. If it was true, it's now false. If it's false, it's now true. Okay, so it's the opposite, which sometimes we might need to do. And is an operator that, as the word suggests, if I have two propositions or two inputs, A and B, then we'd say the expression A and B is true or is on only if both A and B are on or are true. Okay, so the logical operator and is just the English word and for the most part. And what I'm just saying here is, okay, if I have a circuit that says, or I want to know when is A and B true, I'm going to say, all right, well, that's true only when A and B are both true. So obviously it would be false if either one of them is false. Or is another connector that we might want to use. So how do we know if A or B is true? Well, again, it's just mostly the English definition. I'd say A or B is true if A or B or both of them are true. Okay, oh, that's this word. That both probably shouldn't be there. I'll cross that out real quick. Nope. Okay. So we say A or B is true if A or B or both of them are true. Okay, so it's just sort of like in English, right? If I say, um, "Are you buying a coffee or a tea?" You'd say, "Yes, I'm buying a coffee or a tea." If you're buying a coffee or a tea, or maybe you're buying one of each. In all cases, we would say, yes, I'm buying a coffee or a tea. Okay, so again, these two are mostly just sort of the regular old English definition of those words. Okay, the only kind of stranger character, I guess, here is what's called exclusive or it's usually pronounced just XOR. So what's true about that? So maybe the name is suggestive, right? Exclusively or, meaning when is A X or B true? Only if A or B are true, but not both. Okay? So or and XOR are obviously very similar, right? But A or B is true if A is true or B is true or both of them. But XOR says you have to have just one of A or B be true. In other words, the other one has to be false. Okay, so you can't have them both true. All right, so these are the just general descriptions of our four main operators. So let me show you truth tables of each one. Um, so not, right, so the not operator. So if I say A is false, so this is our first example of a truth table here. So I say, all right, if I want to try to make the truth table for not A is what I'm trying to do here. I think, oh yeah, right there. Then I might say, all right, so A is my only proposition, and A could be either true or false. So I listed here, I said, okay, it could be false or it could be true. We listed in either order. So what would I say about not A in both of these two cases? I would say, well, all right, if A is false, then not A is true. If A is true, then I would say not A is false. Okay, so not is the thing that just flips, right? It just takes one and flips it to the other, flips it to whatever it isn't. The and, as I mentioned a few minutes ago, just says if I have two inputs or two propositions or variables, this is true only if they're both true. So for example, right, if A is that you've hit the number 5 key on your keyboard, and B is that you've hit the shift key, then A and B would actually sort of describe when do I make the percent sign, which if you look on your keyboard, the percent sign is above 5, right? So the logical circuit, so to speak, of how do I know when to do the percent sign is I would say, oh, that's when A and B are both true. Namely, I've hit the 5 button and the shift key at the same time. That's my trigger to say, yes, do the percent sign right now. Okay? So what's the truth table look like for A and B? So I say, all right, let me list my propositions, A, B, and then here I want to list all the combinations of true, false. So now, as you might see here now, I'm up to 4 rows, I guess, right? But if you think about it, A and B are both either true, they could either be true or false, right? So if you think about it, there are 4 different combinations of true, false for A, for two propositions, in this case, A and B. They could both be false. A could be false and B could be true. A could be true and B could be false, or they could both be true, right? So these are my 4 cases of if I have 2 propositions, I have to consider 4 cases. All right, and in each case, I want to evaluate, okay, so what would happen with A and B? In other words, would it be true or false? So in each of the 4 cases, each of the 4 rows here, we should just be able to think about this and hopefully come up with the answer. So if A and B are both false, then A and B is also false. Remember, the and is true only if both inputs are true. So in other words, if A and B are true, that's the only way you're going to get A and B to be true. Okay? So if they're both false, then of course this is false. And if either one of them is false, in my next 2 rows here, right, A is false here and B is false here. So since in both of these cases, one of them is false and one of them is true, this is false because it's not true that A and B are true. The only time you get true for A and B is when they're both true. Okay? Or, as we said before, right, or is true as long as A or B or both are true. So or is sort of almost like the opposite of and, right? Because and is mostly false and only true if they're both true. Well, or is only false if they're both false, right? Because again, as long as one of them is true, I'm good to go. It's true. So take this example, right? If A is the event hitting the right arrow in PowerPoint, and B is the event or is the proposition clicking the mouse. So you may or may not know this, right? But either of these 2 actions will cause me to move to the next slide. I'm usually hitting the right arrow, I think, but if I click on the screen, it'll also move me to the next slide. So here I would say, how do I know, how does PowerPoint know when I want to go to the next slide? It's looking at the circuit, in this example anyway, A or B. Because if that's true, I want to go to the next slide. And if that's true, I want to go to the next slide. I guess I could be doing them both at the same time, although that probably would cause me to move twice. But, right? So if either of these is true, this is how I know I want to cause this action to happen. Okay, so what's the truth table for the OR operator? Remember, this is true if A is true, or B is true, or both of them are true. So if you look down here now, right? If they're both false, if A and B are both false or turned off, then this is false. Then it's not true that A or B is true because they're both false. But in each of the other three cases, at least one of them is true. Here, A is false, but B is true. So yes, A or B is true. Yes, because B is. And here, this is true because A is. And they're both true in the last case, but that's still okay. That still says, yeah, okay, but A or B is true because they both are. All right, exclusive OR is the odd duck again that says, what if you want to only have true if one of them is true, but not both? Okay, so exclusive OR is the same as OR. It's just that it's false in the case that they're both true. Okay, so here's the best example I could think of on the keyboard is how do I know when you want to capitalize a letter? Well, one way that you would capitalize a letter is if the caps lock is pressed. And another way you would capitalize a letter is if you hit the shift key. But if you hit them both at the same time, you, I think, actually just get a lowercase letter because it thinks you have the caps lock on, but then you're shifting, which means that I believe it makes it go back down to lowercase. So in this case, XOR is the perfect connector, because how do I know when I want to make a capital letter? If this is true, XOR this is true, that's when I want to do it. That's when I want to say, yes, it's true, you should capitalize this letter, is when either one of these is true, but not both. So that's XOR. Right? So the truth table is exactly the same as the OR that we had up here a second ago. The only difference is that in this case, where they're both true, I actually say no, this is false now. Okay, so it exclusively has to be one or the other that's true, but not both. Okay? Okay, so here's sort of a recap of the true-false stuff for just our standard 3, in this case, or 4 operators, if you include the not operator. Okay? So, all right, so this is making truth tables, which is what we were just doing, is not, well, it's not exciting ever, but it's super not exciting when it's just the operators themselves. So what are some at least somewhat more interesting questions? Maybe it would be for us to construct the truth tables for maybe these expressions or these sentences down here. So we're going to do these together in just a minute. But just a reminder of how am I going to do this? First, make columns for all the variables, and maybe also make some columns for some of the more complicated connectors that might be in there. I'll show you what I mean by that. Determine how many rows you need. So remember, the number of variables you have, you need to do all the possible combinations of true, false. So if you have 2 variables, like we've had in our last couple examples, we needed 4 rows, because there were 4 different combinations of true, false. But if there's 3 variables, or 3 propositions, like in my third example down here, I have A, B, and C, there's actually a whole bunch more combinations of true, false that I'm going to need to investigate. And in fact, if you think about it, surprise, surprise, it's binary once again, that since you have 2 options for each thing, it could be true or false, you have 2 to the number of variables, cases or rows, in our truth table. So if I have just A and B like I do in my first 2 examples, I'm going to be able to get away with 2 squared, or 4 rows. But if I have 3 propositions, like I do in my last one, I'm going to need 2 to the 3, or 8 rows. Okay, so we'll see that when we go to make our tables. And then I want to define all possible sequences for the truth table, starting with all the variables and ending with all the variables true and ending with all the variables being false. So we're going to build up um, our logical sentences then when we go to fill in these tables, just by sort of asking ourselves, all right, in all of these cases, what my results here would be. What would they be? True? Would they be false? And so on and so forth. Okay. All right. So let's try this. I think I can do the first couple ones here. So let's say we're trying to make a truth table for this expression, for this sentence, A and not B. All right. So right? So I'm trying to just say, so what is the purpose? Or what am I trying to do here? Is I'm trying to sort of investigate and say, all right, A and B are things. They're propositions. So maybe A is some key is pressed, and B is some other thing. The monitor is on, or something like that. So I'm just trying to sort of investigate. All right, this sentence that somebody wrote down randomly, A and not B, when is this true and when is this false? So in other words, for the different combinations of A and B being true and false, how would I evaluate X, as I've called it here, which is this sentence? All right. So if I'm trying to investigate this with the truth table, I say, all right, I'm going to take my propositions A and which I just have two of them here. I just have A and I've got a B. So I'm going to say, all right, let me list those, A and B. And then I'm going to list all the combinations of true false that exist for A and B. So there's only 4 of them, and here they are. And now I just want to ask myself, all right, well, what would, in this case, I'm just have really just one big step here, which is to say, all right, what could I say about this expression, A and not B, in each of these 4 cases? So I'm going to fill these guys in. So remember, if I'm thinking about this, I'm saying, all right, I've got 2 operators in here, right? I've got the AND operator, which remember, AND says, if this is true, your expression is true, if both sides are true. Right? So remember, the AND operator says your whole sentence or your statement here is true if both sides are true. Okay, and it's false otherwise. So you might start off by just saying just that, right? So how do I know if this sentence, this statement over here is true? Well, it's only going to be true if that's true and if this thing over here also is true. Okay, so the only way I'm going to get a truth from an and is if both pieces are true. Okay, so what does that mean? That means A has to be true, which means I'm in these 2 cases. But not B also has to be true. So remember, not B is sort of the opposite of B, or the not flips it, right? So not says, okay, let me switch it. So how is not B true? Well, B itself would have to be false. So if B is false, not B, remember not is flips it, would then be true. Oh, okay. And the only way I get true from an and statement is if both pieces are true. I think I maybe just sort of hopefully did this, right? The only time I'm going to get true here is if A is true and not B is true, which is equivalent to saying B is false. So I think if hopefully you're following along with me here, this case, my second row here, is the only time I'm going to get true. So if I'm trying to fill in my answers here, I get true if A is true and B is false. That's the only way I'm going to get true here. And that's the only time an and operator is ever true, is if both pieces are true. So it must be in the other cases, the other 3 cases in my chart here, I'm going to get false each time, right? Because at least one of the 2 sides of my and statement is going to have a false in it, right? One of the 2 pieces, or both of them, in fact, in this case, they're both false. But the point being, right, how do I describe this circuit? I'd say, okay, this logical sentence here I might say at the end, all right, so what is X, right? Or how do I sort of describe the behavior then of X, this whole thing? I would say, all right, so X is true only when A is true and B is false. Might be just my shorthand way of describing what's X. And again, I don't know what action that might correspond to, but you can think of situations where maybe that's the only time you want this to be on or to be happening is maybe just in these moments where A is on and B is off. That's the only time you want to do this. Okay, so I don't know. That's sort of I don't have anything more to say about exactly how to fill these in, but hopefully, rewind me if you're like I don't know where these F's and T's came from, but just sort of try to analyze the question and just kind of break it apart. The chart is kind of nice because it does help you kind of just break it into cases so that you can kind of think about each one separately. All right, so let's maybe try one more here. um, so this says I want to try to analyze this sentence, this statement, which is not A exclusive or B. Okay, so this is a little tricky, right? So I'm going to do two things, right? I have to think about the opposite of A, or in other words, not A, and then I have to exclusive or, which we'll have to remind ourselves of what that means, with B. All right, so as I'm trying to study this, I see I've got two propositions. So I start with my usual starting point, which is to say I've got A and B, and below here you see the usual four combinations of true false that I might have for A and B. So I want to come over here and think, all right, so how do I evaluate what if this is true or false in each case? Well, again, I might just sort of go to the main connector here, which is the exclusive or. And remember, exclusive or wants one of them to be true, but not both. Okay? So you might say to yourself, all right, exclusive or is true, so I'm going to put a T over here, only when exactly one of the two pieces is true. So we could sort of do this case by case maybe. So either like before, it was easy to sort of say, well, let me just pinpoint the one case and then fill the rest in. But maybe for this one, let's try the other way, which is to say, all right, I'm going to go row by row and evaluate, is this true or not? So if A is true and B is true, that's my first row, then what do I get? So A is true, B is true. So not A is false. All right, so in my first example, true, true, this is false, and B is true in my first row. So I'd get that. I'd get false, true. Remember, exclusive or is true when one is true and one is false, basically, right? So it only wants one of them to be true. So actually, this is a case where this would be true. So I'd put a T here to say, yes, this is going to be turned on, so to speak, when they're both on. Which I know is like, say, wait a minute, exclusive or is only true, is true when one of them is. But remember, the A over here got negated or got nodded. So this is, for this setup of A on and B on, or A true and B true, this will flip to false, and this is true. So I get one false and one true, and exclusive or says, yes, I'm going to be activated when one is false and one is true. Okay. All right, so let's go to maybe the next row. So A is true. So this is still false, because not A is the opposite of A. But now B is false, which means my T that was here, I'm going to cheat here like you guys do on true false quizzes, and say false now, right? So my second row is this. So I have false, exclusive or false. Oh, wait. Okay, so neither of them is true, which means exclusive or is false. Remember, exclusive or wants one true and one false. So in this case, I would say my sentence, Y, is false in this case. All right, so then I'll try my last two guys down here. So false, true. Okay, so A is false, B is true. So I'm going to do this sort of underneath maybe. So I'm done with that stuff up there. So A is false. So not A would be true. Okay. And then B is true in this case. So I'd get a true here. Okay. But remember, exclusive OR wants one of each. So true, true, which is what I'd be looking at, that's false for exclusive OR. Exclusive OR says just one or the other. So this would also produce a false or an off, so to speak, for this one, in this case. All right, then I got my last case here, which is false, false. So A and B are both false. Well, if A is false, then of course not A is true. And then B is false in this case. So let me change my T to an F. So my last case, I end up with true, exclusive, or false. Oh, okay, so that's good, right? So one true and one false. That does make exclusive OR true. Okay, so my truth table analysis would be these guys over here. But I might try to be a good person here and look at this and say, okay, so what the heck, what is this then, right? Or what's why? How could I sort of summarize when is it true and when is it false? Well, if you think about it, this is true. So my result here is true when A and B are the same, and it's false when A and B are different. Okay? So, right? So there's sort of, ways of sort of trying to summarize and make some logic, no pun intended, out of these sentences, right? So I think that might be a reasonable sort of written summary or just discussion of what is this circuit trying to do, or when is the circuit on and off? Well, it's on if A and B are either both on or both off. And it's off if they are not the same. So one's on and one's off. So actually, if you think about it, exclusive OR was actually just the exact opposite of this, right? So the exclusive OR chart that we did a few slides ago was false, true, true, false. So it's actually just sort of the opposite, you could say, of exclusive OR, which hopefully kind of makes sense because the not is sort of the opposite. Okay, great. Okay, so that's another example of that. So if you have a longer one, there's a couple things or a couple of strategies that you might employ. So here I think I forgot to include a column for C. So I'll do this one separately, just in a quick secondary video. So you could try this one if you're feeling ambitious right now. But I did need to make a larger chart for this one. So I'll post just a mini video of me doing this one after this. So okay, but of course the question is, right, why are we doing this and why is this useful and things like this. So well, if I want to try to sort of say, all right, and I've alluded to this already, right, but the circuitry is going to help us actually make actions happen, right? So how does your computer know to make, in this case, maybe the dollar sign? Well, mechanically, I have to know when should I make this. Yes, there's an ASCII code for the dollar sign. So yes, that is what's sort of stored in memory. But, right, I have to sort of code, and by code I mean make a circuit that would say, well, when should I do dollar signs? Should I just do dollar signs all the time? In which case they would just be produced on your screen at will. No, I need to have a logical moment of something being a circuit being connected and turned on that says, oh, okay, that's when I should make the dollar sign appear. And I think this is exactly how that would happen, right? If A is that you're pressing the 4 key and B is that you're pressing a shift key, then A and B, which would be the circuit that I would make, would be exactly the right logic to say when should the dollar sign appear. In other words, when should it show up on the screen? Oh, well, if that circuit is completed that says A and B are both true, that's when I want to do it. Okay, so and of course we obviously that's a simple thing, right? That probably isn't like, oh my gosh, I wondered how it knew to do a dollar sign? It's like, well, because you're physically pushing the 4 key and the shift key, right? So, I mean, that's not a huge mystery, I guess. But yes, how is it doing all this other stuff? I mean, much, much more complicated circuits. But to be honest, they're all more or less made out of these 4 guys that we talked about, right? So in reality, what are these guys made out of, right? So these connectors, as we've been calling them, or operators, are actually also just built out of transistors, which we won't look at any one of them in particular, but you can simulate, and by that I mean actually construct, these logical mm, connectors just by making just with some transistors. In other words, you would put things, have inputs into these operators, which would, again, depending on whether they were turned on or off, true or false, like we explored in the truth table, the desired output from these guys would be what was in the sort of last column of our truth tables. Okay? So, for example, um, any proposition, like we'll keep using this dollar sign example, the shift key and the 4 key, well, there's wires, as you probably know if you've ever broken a keyboard. You know that connected to the bottom side of the keys on the keyboard are wires, right? And when the key is not pressed, those are turned off. In other words, those are false. So is the shift key pressed? Is the 4 key pressed? Well, if you're not pressing them, then false. Those are both false propositions. But when you push the keys, the false turns to true. So what happens? Well, there's wires sticking, or wires connected to every key. So if you push the 4 key and push the shift key, you turn those two transistors on. And so those are being fed literally into an AND uh, circuit, or an AND transistor. And so why does a dollar sign appear? Well, because you've turned these two things on. They're being fed into an operator that says, I'm going to turn on only if both of my inputs are yeses or trues. And so then electricity will spit out of the AND gate, of the AND operator, and a signal is then sent to the screen that says, make a dollar sign appear. And that's it. That literally is exactly how this is happening. So I don't want to do it because I don't want to mess with my presentation right now. But if you push the shift key and push the 4 key, why does a dollar sign appear? It's all mechanical. You've completed a circuit. It's the same thing as flipping a light switch. Why does the light in your room turn on when you flip the switch? Is you put 2 wires together. In this case, I put more than just 2 wires together. I turn these 2 switches on. And since these 2 switches have wires sticking out of them that are fed into an AND circuit, that AND circuit processes, which is off right now, it's off, it's off, it's off, but as soon as you hit these 2 keys, these are both turned on. The AND gate actually is now also activated, and the computer's constantly listening to say, should I do a dollar sign? Should I do a dollar sign? Should I do a dollar sign? And the answer is no, 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 until I hit both these keys. And for a brief moment, the answer is yes, do it. And a dollar sign appears. All right? So it's kind of, I mean, I don't know. Maybe it's not that, maybe it's not that exciting. It's just a damn dollar sign. But it's pretty neat that this is actually physically exactly what's actually happening. Okay, so we can help sort of visualize these circuits, um, uh, which are actual real things, right? So when I say an and or an or an exclusive or and things like, those really are sitting under the keyboard, right, in your computer or in your phone. You've got those transistors are actually in there. They don't say like, oh hi, I'm an and or anything like that, but they're in there. I promise you. And if one of them gets wet, right, why does your computer break or do weird things when it gets wet or something? Well, water is not good, of course, for electricity, so it kind of messes up these logic operators and makes them do screwy things. Water conducts electricity, right? So if you get something wet, all these switches, all those light switches, which were probably supposed to be off because you weren't doing anything, when you put water on it, it connects all of them. So things go crazy because it's like, oh, he's pressing the 7 key and he's pressing the shift key and he's pressing the escape key and all these other things which on any normal basis are false, all of a sudden all become true. And of course, your computer's freaking out because it's like, oh my God, I got to do all these things at once. And it fries itself. And that's why when you spill water on something, it breaks, right? Something electronic, it breaks because you fried the circuits. It's trying to say, do everything all at once, basically. And it physically, catches on fire, or well, it doesn't actually, but it melts, right? And that's why it burns up. Okay, anyway. Um, right. So the actual circuits that are in your computer are physically, these are real things. Um, right. And each proposition, how do we think about these propositions of, am I pressing this key or whatever? You can think of them as light switches or sources of electricity. They're either on or off. And these are quite literally fed into these logical operators. We sometimes use the term logical gates because the idea of a gate is sort of like it either lets something go through it or not, right? That's sort of the idea of a gate in a fence or something, right? It's either open or closed. So we sometimes use the term gate to mean and or and those guys. Um, so the result, so how do I sort of view the result? Well, in our real world, we'd say, well, the thing happens. In other words, the dollar sign appears. That's the result. But if we want to try to sort of study these circuits just in a sort of play sense of the word, we might sort of say, well, how do I know if the um, result is happening or not? Maybe think about there being maybe a light bulb at the end of the circuit. In other words, coming out of the gate or coming out of the logical circuit is maybe a light bulb that if you have a true in your truth table, the light bulb would be on, and if you have a false in your truth table, maybe it would be off. Okay, so there's symbols that are standard for our friends, for our gates. So the and gate or the and logic symbol is this character. I don't know how to describe that exactly, but that shape is, if you see it in a picture, means and. So again, the idea is that physically, and this is real, right? Physically in your computer, these are wires. This is connected to some proposition, some yes, no, or true, false, and so is B. And these are like light switches that could either be turned on or off. In other words, you could have electricity flowing or not electricity flowing. So it enters this gate, which in this case we're looking at and the wire that's coming out of it, which is over here, is again either turned on or turned off. Or in other words, electricity is flowing or electricity is not flowing, depending on, this logic stuff that's here. So this is physically, I mean, it doesn't look cute and it isn't, this cute shade of lavender. I mean, that's not what's actually in your computer, but it is in terms of the actual wiring of this coming in, some transistors, and the appropriate logical stuff coming out. Okay? Anyway, so this symbol here represents and. This curvier symbol represents or. Okay? The triangle represents not. Okay, so this is our flip, right? This is our do the opposite guy. Oh, I should say, I'm sorry, let me flash back real quick. This symbol, I don't know what you want to call that, is the symbol for and. So you don't have to, I mean, this stuff isn't all that important. You could just write the word and it's much more useful in many ways to do that. But in case you see it somewhere, the little triangle guy pointed this way is and. If you flip it upside down, it's or, so it's more of a V. That's the equivalent of or. Not is usually represented with a squiggle or a tilde. So A, right, and the gate symbol is a triangle for not. And for exclusive or, it doesn't have a cute symbol. And this is the gate icon, I guess. So it looks like the or guy, right? It looks like this curvy thing. But there's this extra little, I don't know what I want to call that, crescent, I guess. That indicates that it's exclusive or as opposed to just or, right? That was the or picture. Exclusive or. Similar, but slightly different, right? Okay, so this is the last slide, I think, in this video. What should you maybe do? So aside from doing some truth tables in the homework and things like that, and in terms of trying to interpret, what's the physical meaning of these things, one thing that's neat to be able to do is to play around with actually building these circuits. And again, if this was a physics class, we might physically bust out some wires and actually um, and actually build these things and put light bulbs and things. Okay, that's an awful lot of work, though, right? So how about instead we play around maybe with an applet that lets you kind of build these circuits and maybe try, if you would, to maybe build these 5 examples. These are the ones, or most of these are the ones we did in the lecture here. And, play around with it, right? So this is sort of about experimenting a little bit. And if you're in the notes right now, or if you're in the PowerPoint, when you click on this, it'll load the applet. I'm going to make a separate video of me doing these problems and doing the circuit applet, just because this is already a long video. So either pause me or whatever. This is the end of this video, so I'm going to stop talking now. But watch the next video, which will be of me here, and I'm going to click on this and then build these circuits. So first, watch it, and I'll give you a little orientation of what this applet's going to do, and then try these, and I'll build these as well.